So we have x here, Poisson lambda. We're going to let mt be the MGF of this variable. And then we're given this cumulant generating function, which is defined as the following, which is the log of this MGF. And we also are given that when you expand this GT, you get some sum that looks like the following. And this sum starts at 1 because this when g of 0 is 0. So we're asked to find the coefficient here, Cg, which is called the cumulant of x. This looks like an unusual question, but let's nevertheless proceed as we would normally, which is, to find the MGF. I mean, we know what it is by the book, but let's just calculate it again, and then we take the log of it, and then see if we can somehow make this thing into that thing here. Okay, that's our overall strategy here. So the MGF of x, which I just called mxt to make it clear that it's the MGF of x, by definition is the expectation over e to the t of x. And now we're going to proceed by taking the expectation over this random variable, and by lotus we have now a Poisson distribution, which means that we will have to take over sum over its support, which goes to infinity, and we then take this transformed version. So this is lotus here, means that we can take this whole thing, e to the t of I, and then we take the PMF of this, it should be the e of this variable, e to the lambda. All right, so far so good. Let's now think about how to actually calculate this thing. Well, we can move, we can move this term out, and we can move this term in here. Okay, and then we going to say that that thing is a Taylor expansion and basically retrieve a term that is the exponential of those coefficients in there. So this is 1 minus lambda. We have the sum I0, and we have I to the factorial there, and then we're going to take e to the t lambda I, like this. And in the next step, we're going to use the fact that the e to the x is equal to the sum over I to 0 from I to 0 to infinity xi I factorial. A lot of i's here. Okay, so, and we see now that this thing in here is in fact x. Okay, so we're going to use this and just write e to the t lambda. All right, and that can be simplified a little bit. So this is now e to the e t lambda minus lambda. We factor out lambda, which gives us e to the t minus 1. All right, we just derived the MGF of the Poisson to start off. A little bit of a warm-up. Now In the next step, let's take the log of this MGF and slowly and gradually start comparing it to this term here. So I'm going to take the log of mx of t like the following, and that yields the log of e to lambda e t minus 1. And that is, so we get the e canceling out with the log. We're left with lambda e to the t minus 1. Okay, this looks all fine. Now, and the next step, and this now gets us to a situation where let's write out g to the t here, g to the t. So what we want is something like so e to the g, the sum over I1 infinity cj j factorial t to j. Okay, like that. I'm going to move it down here. Now this looks like a stretch. Like how do you move from this term here into this term here and start comparing this term here and start comparing these terms? Well, it turns out that you can now use the reverse of this Taylor. So we're going to put it back again here and see if that sum somehow compares to this sum here. That seems like a good step. So let's do that. So we do Taylor expansion lambda, and now we have this sum from I to 0 to infinity, and what we have is t is this x I factorial minus 1. All right, this looks now pretty familiar, right? This is not very far away from that factor inside there. Okay, but notice that this sum starts at 1 and this sum starts at 0. So let's move that one step ahead. Let's see what we get. So lambda, the sum I equals now 1. Actually, let's put it here because we've done the version where the first term in the sum is a 0. So 0 factorial, that's 1. T to I is 0, that's also 1. So the sum starts at 1 plus now infinity t to I factorial. We have the minus 1, and now we can cancel the ones cancel, the ones cancel here. So this cancels, that cancels. So what we're left with is now lambda, the sum over I equals 1 to infinity ti factorial. And now we can move in this lambda. So let's move this lambda in. Let me just copy this and duplicate, move it down here. Let's move this guy up down here. Let's make some space. So now we have this lambda moving in, and this is now exactly in the form of this term. So it must mean that Cj, although it moves from I to infinity and has different terms, you might guess, in this particular case, it is equal to lambda. So all this implies that Cj equals lambda. So that is the coefficient of Zj, and that is what we were asked to find.